If we have a circular or spherical lens with parallel rays striking the lens from a medium where N is about 1, air, most gases, a vacuum, doesn't matter too much, but N is approximately 1 out here, and with N approximately equal to 1.33 alcohol or water inside here, then, as we've seen, the rays will bend, and the rays that hit close to the central ray, now the central ray is the one right in the middle here, okay, the rays that are close to this central ray will all tend to focus very, very near the same point. And we can find that point by just tracing a single ray as it gets refracted at the lens surface and goes over and meets the central ray. Now that's the point at which all the other rays will focus. And we'll see some details of that shortly. We've of course observed this. And we've done some analysis of these angles, the way the refraction occurs here using Snell's law, and the fact that a normal is going to be radial, going to be a radial line at every point on the surface here. If we have a mirror, then parallel rays come into the mirror, and the rays close to the central ray, and the central ray is the ray that comes in and gets reflected directly backwards, just as the central ray over here is the ray that comes in and moves through the lens undeflected. The central ray here maintains the same direction also, but in this case it's reflected. The rays close to the central ray on a circular or spherical mirror will all strike at the same point, or very near the same point. Now as you get out away from the center, they don't quite strike at the same point. That's a phenomenon called spherical aberration. The rays close to the center focus very nicely. Rays further from the center don't focus as well. Now I'll also mention if the mirror is parabolic instead of spherical, then there is no aberration and all the points focus at the same point. This is also a phenomenon we see with satellite dishes which are reflecting microwaves. You put the receiver at the focal point so that all the rays that come in from the satellite, which are parallel, strike the same point. And that mirror is parabolic in its cross-section, not spherical. A spherical would work all right, a spherical dish, but a parabolic dish is much more efficient. The nature of the reflection is such that the angle of the incident ray is equal to the angle of the reflected ray as measured from the normal. Remember, for a spherical mirror, the normal is just a radial line from the center. For a parabolic mirror, of course, you have to do a little more mathematics to determine the direction of the normal. So we have an incident and a refracted angle here, and they're equal in a reflection. And of course, the mirror at this point of contact is essentially the same as a flat mirror that has a direction tangent to the circle. That's all a simple consequence of the geometry of the circle, that a tangent line is always perpendicular to a radial line, and gives us the nature of the reflection here.